In this lab, we will analyze the motion of a falling soccer ball using tracker data, and then build two computational models with and without drag included. We will compare the experimental and computational positions on the same graph to understand which is the most accurate. We will then examine how the drag force affects the velocity of the ball in a velocity versus time graph of the two Python models, and then connect these values to real-life motion. In my video, I will be analyzing the motion of a soccer ball as it falls from about 1 meter in the air. The ball's position starts at the origin and ends at about -1 meters in the y direction. The positive y-axis points upwards and the negative y-axis points downwards. The origin is defined as the position at which the ball is initially dropped. It's important to note that the tracker video was taken in slow motion and runs for 3.167 seconds, while the actual motion of the ball falling lasts for 0.429 seconds. We will need to use the value of 0.429 seconds in order to get accurate calculations in our models. To begin calculating the position on our falling object, we must first consider the net forces acting on it. At first we will ignore air resistance and drag, but we'll talk about those forces later. The only other force acting on our system is the force of gravity, which we can easily calculate using the mass and the gravitational constant g. Then we can use our fundamental principle of Newton's second law to determine the final velocity over a certain time interval. Here I did an example of what the final velocity would be over the first time interval we calculated. Lastly, we can use this velocity to determine the object's final position. We can substitute v final for v average in the position equation because the net forces over this time interval are not constant. To start off our computer model, we need to define some initial conditions that we discussed previously in the video. Just like in the tracker data, our delta t will be 0.033 seconds. The gravitational constant g, as well as the j-hat position vector, are also defined here. One of the most important parts of the code is the calculation loop. Like we discussed in step 1 of the calculations, this part of the code is for defining the F-net of the system. This line is where we define Newton's second law over this time interval. And here, as in step 3, we will update the ball's position by using the velocity described by the previous line. When we graph the model positions and the experimental positions on the same graph, we will get something that looks like this. It appears as though the model is less accurate at first, but then becomes closer to the experimental values as time goes on. Small discrepancies in initial conditions could be the reason why these two curves differ a little bit at first. However, we must now discuss the force of drag that we ignored earlier, as it does have an effect on the system. The only process that will change in our calculations is how we determine the net force. To determine our new net force, we will add the force of drag with the force of gravity. The drag force is calculated as b, the proportionality constant, times the ball's speed squared during this time interval. After a period of time, the drag force will equal the gravitational force and the F-net will be equal to 0. The ball will then fall with a constant terminal velocity. To include drag in our code, we just need to alter the calculation loop. We will use the magnitude of the ball's velocity, or speed, squared times b, the proportionality constant, times the unit position vector j-hat to get a drag force. Now our new F-net will include the drag force and the gravitational force. This is what we get when we add the drag position data to the graph that we discussed earlier with the experimental and model positions. It is clear that the model that does not include the drag force matches the ball's motion most accurately. It could be that the equation we used to calculate the drag force was incompatible with this specific situation. However, the position values don't tell us the whole story of the ball's motion. Now we need to investigate into the velocity versus time values of each of the two models. We can compare the computer models with and without drag more accurately when we graph their velocities versus time on the same graph. The velocity in the model without drag seems to decrease constantly, which means it's accelerating in the negative y direction. However, the model with the drag levels out around -2.22 meters per second. The velocity that the drag model levels out at -2.22 meters per second is the terminal velocity that we discussed earlier. Without a terminal velocity, as in the model without drag, the object would just keep accelerating and accelerating downward. From the motion of falling objects that we see in our everyday lives, we know that this continuous acceleration would be unrealistic. Even if the ball was thrown downward at a great speed, its terminal velocity would remain the same, since it's related to weight, not initial condition. Even when thrown downwards at 5 meters per second, The velocity versus time graph shown on screen indicates that the terminal velocity still levels out at around negative 2.2 meters per second.